So yesterday on example 3, we kind of have some mathematical synonyms now. And example 3 gave us the third one. Solving a differential equation involved the process of finding the antiderivative, okay? And today you're going to learn the third one, which is, I'll give it to you now, it's integration. So when we solve the differential equation, just to recap, we have f prime equals 3x squared plus 1. It's an equation with the derivative, so that's the differential equation. Solving it means getting back to the original function from which it came. So f prime gets back to f, f double prime would get back to f. They all get back to the original. The general solution involves plus c if we're given an initial condition. Once we find the general solution, which would be the first step, we then use the value of the ordered pair to find c, and then we rewrite our particular solution using the value of c we found. Okay? The process we're going to learn now is called integration. And integration is going to be a word that I use interchangeably now and almost more exclusively than its perfect mathematical synonym, which is anti-differentiation. So anti-differentiation. There you go, long word. So when you find an antiderivative, it's like finding what's going to be called the integral of an expression. Antiderivative, integral. Anti-differentiation, integration. Now there's two types of integration. We're going to focus right now on what's called indefinite integration, as you saw at the onset of the section. Indefinite integral just means that our answer, which is an antiderivative, is going to be indefinite, meaning it's a function of x. It's a variable function. Okay, but we have a new symbol that comes along with integration, and it's called the integral symbol, and it looks like an elongated S. And the reason it looks like an elongated S is for a very good reason. It's going to end up being, as you'll see in the next section, short for the sum of a bunch of areas. And so it's kind of morphed into a symbol. Okay, so this now, the integral symbol, becomes a verb. Okay, and we have a verb already for the derivative. When you see the derivative with respect to x, something like that, you know to take the derivative of what follows with respect to x. Okay, so this is actually the verb, take the derivative of what follows, and the dx means with respect to x. We have another one now that I'll put right here. It's going to be the following. It's going to be the integral of what follows with respect to x. So we have another verb now. And those are separated, okay? The dx is still going to be your variable now, what we call of integration, not your variable of differentiation. And the integral is the verb that means take the antiderivative of what follows with respect to x, okay? So the reason we have the symbol now is so we can write it like that and not have to put all the instructions like find the antiderivative of the following expression or solve, find the general solution. We can just write that and say evaluate, and you know what to do. Okay, so let me kind of show you what it looks like, because we know we can take the derivative of both sides of an equation. We can now take the integral of both sides of an equation. So let's say we start with a real simple differential equation, dy dx equals f of x. This is called Leibniz notation, right? Our old friend Leibniz. And what's nice about Leibniz notation is you can treat those numerators and denominators as independent quantities, and you can multiply both sides by them if you needed to. So here's what we're going to do. If we want to solve that, we're essentially going to take the integral with respect to x of both sides. Okay? Now, when we do the integral of both sides, we split it up. The integral symbol itself becomes the left bookend, the instructions, find the antiderivative of what follows, and the dx becomes the right bookend. It means of or with respect to x. And so the expression we're finding the antiderivative is trapped in between them. Okay, now what happens on the left side? What is the antiderivative of dy dx with respect to x? It's like y prime, yeah? What's the antiderivative of y prime? We just call it y. So this becomes y on this side, and of course the antiderivative of little f becomes big F, and then we put plus c. So we've been doing this all along, and yesterday we went straight from here to here, but this middle step here is why it works, okay? Because we can now find the antiderivative, or the integral, as I'll say, of both sides. Okay, so just some nomenclature here, some vocabulary. The integral symbol itself is the verb. Find the antiderivative of what follows. The dx at the back, that's your variable of integration. But the expression or the function you're finding the antiderivative or the integral of, we have a new name for it. It's called the integrand. Just like the thing you're taking the radical of is called the radicand. Okay, good. So we have an integrand. The whole thing is called the integral. In this case, the indefinite integral. And the thing you're finding the antiderivative of is called the integrand. Okay, one last note before we get to example 4. We're going to have a whole section on this later on, but when you have Leibniz notation, it's going to be important to show, and I'll show you this, it's going to be important to show the separation of variables, which means you're going to want to get your x's and dx's on one side and y's and dy's on the other. All right, but we're not going to focus too much on that right now. That's coming up later on. All right, so example 4, let's try out the new notation with the skills that we already have, the antiderivative skills. Find the particular solution to the following differential equation, given that y of 0 equals -2. Okay, they didn't have to tell me it was a differential equation. I could have figured that out. There's an equal sign, there's a derivative differential equation, yeah. But it did say to solve it, not just to look at it for a while. So solving it means, in this case, since it's a first order differential equation, we call it, it's the first derivative, it means getting back to y equals. If it were a second order differential equation, as you'll see in the next example, it's the second derivative, we'd have to find the antiderivative twice to get back to y. But in this case, we're good to go. Now, can we jump straight to the particular solution? No. As we saw up here, the step is to first find the general solution, use the initial condition to find c, and then find the particular solution with your c value in there. Okay, so let's go ahead and use our new notation. I'm going to take the integral of both sides with respect to x. I did that, and now I get this. Now, if you have multiple terms, you want to make sure you put them in parentheses. -1 dx. Now, for right now on the left, we're going to leave it like that. Those dx's technically do divide out. Actually, I'll mention it right now. You can either go straight at this point in the game. You can go straight from here to what? What would be the antiderivative, essentially, or the integral now of dy dx with respect to x? It would be y. But what's going to happen later on is those dx's actually divide out, and it turns into this, which is interesting. And your integrand becomes 1. So what would be the antiderivative of 1 now with respect to y? Well, it would be x if it were with respect to x. Now it's going to be y. Yeah. So either way, you get the same thing. You're either integrating a derivative function of x with respect to x, or anti-differentiating, sorry, or you're integrating a constant with respect to y, and you get y. They both give you y. Now, if I integrate on the left side, I'm going to do something this time and this time only. Technically, since I just found the antiderivative, I need to put plus a constant every time you do that. Now, I'm going to need one on the other side, so I'm going to go ahead and call that c sub 1. On the right side, I think I'm ready to go. I have two terms. What's the antiderivative of e to the x? E to the x, yeah. Plus, well, you could wait to put plus c until you're done with all the terms. Yeah, I guess technically they could all get their own plus c. But since we write it as one integrand, we'll save it to the end. Now, 20 is a constant multiple. It goes along for the ride. What would be the antiderivative of 1 plus x squared all to the negative first? Tangent? Very close. Yeah, it doesn't fit a form. I can't expand it. I can't distribute it. So if you want to come off to the side, that's the same as 1 over 1 plus x squared all to the first, and that is inverse tangent. Good. So I'm going to call it arctangent or inverse tangent, either one. Sometimes you do have to manipulate it a little bit to recognize it. Now that we're done with both terms, now we'll put plus c, and I'll call this one c sub 2. Now, we're not done yet because we have to solve the differential equation, which means getting back to y equals. So now it's as simple as subtracting c sub 1 from both sides, and we get plus c sub 2 minus c sub 1. Well, guess what an unknown constant minus an unknown constant is? An unknown constant. So I can combine these two unknown constants and call it new and improved c. There you go. And because that's how it's always going to work, because we're solving for y, you do not need to put c sub 1 on the left and c sub 2 on the right. It's perfectly acceptable if you leave it off the left side where the y's are, and you just put plus c on the right side where the x's are when you're done. But you have to put the plus c on the right as soon as you find the antiderivative. You can't just like manipulate it and then put the plus c at the very end. So you're not going to lose points on the AP exam or my exam if you don't do that. But just realize that that's actually what's going on. That plus c, as you'll see as we go through a lot of problems, it's like a ShamWow C. It's super absorbent. It will absorb all kinds of unknown constants and factors and moistures. Gross. Tapioca. Okay. Any questions on that one? Oh, yeah, we need to find the particular. Thank you. Yeah, we'll squeeze that in right before lunch. So something to the effect that when y of 0 equals negative 2, you got negative 2 equals, now you plug in the 0 for x, you get e to the 0 plus 20 times arctangent of 0. Arctangent of 0 is what? Oh, well, tangent of what number is 0? Here's the graph of arctangent, by the way. I'm drawing it. Yeah, it passes through the origin, so it's 0. So I get negative 2 equals 1 plus c, so c must equal negative 3. The good transition word is so. Y equals e to the x plus 20 arctangent of x, and then finally minus 3. And that is your particular solution. That's the function whose derivative is e to the x plus 20 times 1 plus x squared to the negative first. That happens to pass through the y-intercept of negative 2. Perfect timing. Have a great lunch.